I'm going to talk to you today about gas holder and demolition of gas holders. So we'll start off with a little bit of history of gas holders, their types, and then we're going to go into a case study on demolishing there's a few different types, but mostly focusing on a man gas holder at Battersea. So looking for some pictures and bits for this, I came across quite an interesting paper that I think I've seen before by Dr. Russell Thomas from Parsons Brickhoff, and just pinching one of his images, that shows you quite nicely a good selection of types of gas holder. So you've got the earliest form there, which is a cast iron column, which provides the support or the restraint for the gas holder when it extends out the ground. Then you've got a steel columns around the outside with a tank that goes up and down similarly, but with a steel structure to support it. And then you've got one of the later types, which is the spiral guided form of gas holder. So as that comes down, you can see there the spiral. So as that gas holder moves up and down, it twists. For those of you that don't know what a gas holder was for, or why we had them, or why we no longer need them, there's a few reasons. We used to have more localised production of gas in the country, which meant you needed localised storage. So the way these work is the gas comes in at the bottom and it actually inflates and lifts these tanks up. So they're under a fairly low pressure. Well, I say fairly low. It's significant, but it's nothing like a modern high pressure gas main. So the gas pressure itself lifted these tanks up and down. So you could see how much gas was in it by the height of the tank. Now we've moved to high pressure gas mains in the country. We no longer need this localised storage method and fairly low pressure gas mains. We all run at much higher pressures than we used to. There's another detail of a spiral guided. You can see even a bit clearly there the spiral guided and how as that comes up it twists through the guides like that, and the other one twists the other way inside it. And there's another clearer detail of a column guided holder. That's quite a big one actually, quite a big lump, that one. Looking at a cross section through, they tend to have an in-ground section, though not always, though I would say most of the ones we ever come with. So you normally have a big masonry wall, though this can sometimes be reinforced concrete. Sometimes they've even been post-tension reinforced concrete. The one we looked at Oxford was a post-tension in-ground concrete wall, which was quite interesting, quite slender and quite interesting to work out how to take it down. Then you've got these columns here which guide the different lifts. In here you have typically water and then a dumpling, which is typically made of clay, or at least clay on the outside, and then whatever the ground is inside, that provides a waterproof layer. Then you have your layer of water, and then your gas goes from the water up. So you can see there the gas pipes in and out. So as you imagine, the gas comes in and it lifts the crowns up, then you close the inlet and that gives you a pressurised system that then pumps the gas back out. Or pumps the wrong word, but the pressure pushes the gas back out. And spiral guide is fairly similar, except as we discussed it, the whole thing twists as it rises and falls. What they both have missed here is there's typically a support structure at this level. When this roof truss comes down to ground level, it sits on a support structure because they're very, very efficient designs. These roofs work when they're under pressure, but they tend to sag quite a lot if the gas pressure is removed. So that's why they have a mechanism at the bottom, or a structure at the bottom here for the holder to sit on. Then we have the other type of gas holder, or not the other, another type of gas holder, a Wiggins gas holder. These were quite a lot more recent development than the column guided and the spiral guided we've seen. These are probably the most efficient form. This is actually one in Oxford that we did with John F. Hunt. So inside here, the roof can come all the way down to the, well, not all the way down to the bottom, down to about here on support structure. As the gas comes in, the whole thing lifts up, and you've got a sealing system here and here, and then it goes up to the second stage. And above that, you've got air. They're quite an efficient, much smaller volume required to store the same amount of gas compared to a man holder, which we'll see next. Quite interesting to demolish as well, because again, quite slender, and stability becomes an issue, particularly as these things are often located next to railway lines because historically gasworks had rail connections for when you went back to making coal gas and the likes. So generally located next to a railway, which means you've got additional stakeholder interest from Network Rail, and you've got surrounding properties, etc. These things are very, very rarely in a greenfield site, or even at a site where you can take them down in the most efficient way. There's normally too many surrounding properties to allow you to blow them down or similar. I know there was a man holder on an industrial estate, I think in Port Talbot, I think, that was blown down. But you very, very rarely get that choice with us, or we get involved with, because of the constraints. Then you come on to MAN gas holders. MAN stands for something in German that I'm not even going to try and pronounce for you. If you want to figure out what it means, go and read it yourself. I'm afraid my German is not my strong point. So within a MAN holder, these things are quite big. These things are quite big. Which you'll see on the next slide. Inside here, you have a piston. So this piston that goes across here. Similarly, you have the pipe that comes in the bottom, and then there's a seal there. Gas is the underside of the piston, air is above, and you have vents on the top as well. So as the gas comes in, again, the piston lifts up, but your holder is a fixed volume, and then the piston moves up and down inside it, dependent on the amount of gas that's in there. Interestingly, this one was hit by a Luftwaffe bomb during World War II. Luckily, they'd emptied them. It's almost like they thought about it, and they didn't really want a bomb going off inside a gas holder in central London. So, yeah, luckily they were empty. So I do wonder how they did actually pressurise the gas systems at the time, but maybe somebody else out there knows the answer. I don't. The bomb didn't go off. On the bomb maps, you can actually see the bomb that went in there, and you can see that it was a dud, which was also quite fortunate. But what we did find when we were doing this project is that the truss had been damaged by the bomb, which was quite interesting in itself. So this is now moving into the case study itself. This is Battersea MAN Gas Holder, and also the other gas holders on the site. So you can see there an old wrought iron column guided gas holder, a MAN holder, then there was a cast iron column guided one, and then was another steel one on the site. So it's quite a constricted site, really. If you've ever watched the TV show about Battersea Dogs Home, you've probably seen this appear in the background in the introduction. I think the MAN holder used to appear anyway. This structure is about 90 metres high and about 55 metres in diameter. This is the location of the site. So this is the MAN holder, and then that was the wrought iron one you saw, then that was the cast iron, and then that was a steel one, I think, from memory. Battersea Dogs Home is there, and that's the main lines into Victoria and the different lines that go off around it. So you can see we had network rail interfaces on two sides, and that, as I said, is the main line in and out of Victoria with I don't know how many trains every minute. It's fairly busy. This is the site now. As you can see, it's been developed into, I would guess it's probably accommodation. It might well be offices. I'm not really sure. I haven't been back to have a look. And then you can also see the Battersea power station development, which is actually quite interesting just to have a look at on Google Earth. There's some serious temporary works in there just from looking on Google Earth. So quite an interesting project. So now we're going to go into a little video, because I think it's the best place to start is a video that explains what happened, and then we can talk in more detail about each part of it. So as I said, or I might not have said, we were working for Coleman and Company to do this work. Coleman's have done quite a few of these MAN gas holders over the years. This was Battersea, was the third or fourth one we did. Then we did one more after that, which was Southall, and I think that's pretty much all of the MAN gas holders in industrial or within city centres. There's a few left on industrial sites, but typically speaking, they can be taken out in a different way. So this is one of the in-ground holders being taken down. So that's the cast iron one you can see in the background. Wrought iron over there, this was the steel one, I think, where you can see they've already taken down all the parts. Then there's Clive on his bulldozer having some fun filling in one of the holders. And if you're interested in, you might well be able to find it. There was a BBC Two documentary called The Wrecking Crew around the time this was done, and this project featured on it. And you can see a little bit more information about it, and there's someone on there who really liked cranes from memory. So it's worth a watch. Quite an interesting subject. So you see the big blue one there is the MAN gas holder, and they haven't even started on that. You can see the support structure there, those concrete piers. And then you can see there they're cutting the plate up from a man riding basket. They lift them out. And then there's one being infilled. So these walls here are masonry. In terms of engineering assessment, there's an assessment of how we take these down and the stability of the sections as they're cut free under different wind loadings, etc. But the main engineering on this is the MAN gas holder, which had some really quite serious and technically challenging engineering. You can see the gas holder, the dog in the background there. And here you can see a nice little bit of felling. There we go, donk. And from the other point of view, make it look easy, don't they? And this is a 500-ton crane coming in to lift up the cranes on the roof, which we'll see a little bit more detail on shortly. So cranes lifted up on the roof, and that is what we use to dismantle the structure. There's a pair of those that go up. And there you go, away they go. They start working from the top down. What you don't realise is they're working on a platform that is being supported by an air cushion, effectively, high pressurised air in the tank, pushing the piston up to the roof and then monitoring it to keep it in the right place. So it's really quite an interesting technical challenge to do these. And I wish there was some more to do, but they've all gone now. And the point at which we stopped using the cranes was agreed with Network Rail, where it was considered that the potential for impact with the railway was reduced, and then we just came in with machines and ripped them apart. So you can see there, they've got actually quite, again, they're quite efficient structures. There's no spare steel in these structures. They knew what they were doing when they designed them. And you can see inside there, you've got the piston sitting at ground level, and then the roof, which was cut free, sitting on top of the piston. That roof formed the working platform for the cranes and all the other operations. And the whole thing was just floated on air. Two large blowers that ran 24 hours a day for however many months it was, with full-time supervision and monitoring to make sure that the roof never dropped below a certain point. Because obviously, if you've got a tank structure and you cut the roof free, you've lost quite a large amount of restraint to the structure. So you've then got to calculate where the roof, or how low the roof can drop and still maintain stability of the structure, which was part of our works, which I'll go into shortly. But that's quite a nice video, that one. And again, it's available on YouTube. How do I get out of full screen now? That's the question. There we go. Right. So we've just seen the video, and this is the pictorial version as to how the sequence is controlled. So that's the existing structure. Lift up all the components onto the roof, lift the cranes up, blow the piston up to roof level, cut the roof free, and then start working our way down, dismantling it. So that's just a very much an outline pictorial sequence that was provided with the analysis of the structure. So Network Rail and other stakeholders understood the analysis and what was being actually trying to be achieved. So the starting point for all this is the analysis of the man holder. As I said, if you've got a big tank structure and you cut the roof off it, you've obviously lost the restraint to the top of the structure. So we had to work out how low the roof could drop on the piston and still provide stability to the structure. We also had a look at different options, such as limiting the works to the summer months, because that obviously gives you a lower wind load. However, from a risk perspective, it was decided not to progress with that because any delays to the program and you are in trouble. So we tried lots of different options to work out how far below this level the piston is allowed to sink. From memory, it's about 20 meters or so. As long as it stayed within 20 meters at the top of the tank, we were okay, stability-wise and stress-wise. So a full FEA analysis was undertaken, and that was independently Cat 3 checked by another consultancy to confirm that our analysis was correct. So this is a little bit of a zoom in on the initial drawing there. So crane installation is what we saw being done with a 500-ton crane. These cranes here going up on the roof, and then the piston gets blown up and the roof gets cut free. So that's the bits we're going to look at, the temporary work specifically involved with those. So this was our kind of control drawing that showed all the other drawings that you needed to read this in conjunction with. It showed the basic principles. So on the outside, you have what we call the working platform. Then inside that, you have the jockey wheel platform. So the backstay and the jockey wheel on the crane runs around on that track. And then we had what we called the strong slice. So this was we increased the, or we put a deck in here, which allowed them to get things like generators and other bits and pieces up to the centre here. Because you imagine you're 90 metres up in the air, you need to be fairly well self-contained. It also shows the crane rail position, which sits round there that the cranes themselves would run on. And then the hoists, etc. But that's the basic principle. On top of the roof is what was constructed. So the cranes themselves, we initially designed these for Coleman and Company on a job in Liverpool back in, I don't know, long time ago now. The first man holder that Coleman's did that we worked on them, worked with them, and we developed these cranes, and then they were refined through the different projects to increase capacity, install slightly more modern drive components with a bit more grunt from learning that we had, and also to increase how far out we could reach. So you can see here these cranes were fully designed and then loader tested, and they had a safe working load of 2.5 tons. Out at whatever rate, I can't read it on these drawings, but there's a pair of those up on the roof, and they have a backstay system here which ties back to the center point in the middle of the gas holder. So they're quite interesting little designs. So you've got the two wheels sitting on the track and then a backstay back to the central point on the tank, and that's the principle of how they operate and how they're designed. So that system in the middle there obviously rotates as the crane moves along and round the perimeter of the structure. Now, on top of the crane has to operate on top of the crane rails themselves. Now, the crane rails were a serious design challenge because they had to be light enough that they were manhandleable. They had to be stiff enough for the crane to operate on without significant deflection, and they had to be in sections we could either bring up in the hoist or could be brought up with a smaller crane. So it was quite a challenging item to design. This was, I don't know, we had an initial version on the Liverpool St Helens, which was the first man holder, but Sod's Law came into play, so the geometry of all of the gas holders is different, so you couldn't just reuse the original track arrangement. So this one here was based on the Liverpool track, or Liverpool crane rail, and then we made these node pieces here to extend the capacity. So if you imagine on top of the roof, you've got a series of trusses coming out radially, and each of these sits onto a truss here and here, and then the rail spans between them. Now, this was FEA analysis was undertaken to check the capacities and the stiffness and the deflection under the worst case loading, and then a Cat 2 check, I think, was undertaken on these that was verified to BS 5950 Part 5, which is for lightweight pressed components, and that verified that our FEA analysis was correct. And these were quite light structure. I think they're about 300 kilos, which is not really manhandleable, but it's more manhandleable than was about as manhandleable as they could be and they did manage to move them around up there with skates and little lifting trolleys and things, so they could move them without having to use a crane to place them. And given the spans we're dealing with, which I think was about, from memory, about 8 to 10 metres, something like that, and carrying about 4 tonnes in the centre, it's working quite hard as a structure. And then you have the crane rails in place, so you can see the ones that were painted from the previous contract and the steel ones, which are the new fabrications. And then you can see the crane rail itself has been rolled and placed onto the crane rails. So you can imagine the setting out of these has to be pretty bob on. You can also see the jockey wheel track at the back here. As I said, this is for the backstay, or the jockey wheel of the crane to sit on. When the crane's not loaded, it rocks back, and it sits with 2 wheels on the crane, on the rails here, and then the rear one sits on the jockey wheel platform at the back, and then they can rotate around. And when they pick things up, they rotate forward until the backstay goes tight, and then they load away and do what they need to do. You can also see the working platform here, which we're going to go into in a little bit more detail shortly. And there you can see the cranes and the crane rails up on the roof. A nice little advert for John F. Hunt there on the Coleman's project, which always makes me laugh. So there's the big generators up there sitting on the strong slice. And there's one of the cranes, and you can see the backstay cable there that I talked about that comes back to the centre. And there's one of the hoists. And there's Big Clive. So the working platforms, you imagine that the work that's been done up there is on top of a structure that is quite old, and by National Grid's own admissions was not in great condition. So it was felt that just walking around on the roof was not a good idea, and I can testify to that, having been up there before the working platform was installed. It didn't exactly fill you with confidence, the roof of that structure. So a working platform structure was put in place. Again, this had significant spans and had to be quite lightweight. They all had to come up in the hoists and to be constructed. And so we used lightweight C-section purlins, steel spreaders between them, and then we used plywood sitting over weld mesh, which gave us the sort of capacity we needed. Got to bear in mind this all had to be cold cut because of the hazard of a fire. Because there's a lot of bitumen sealant used on these, and there's oil-filled seals inside between the piston and the wall. So fire is a very, very real likelihood on these tanks. You don't want to be 90 metres up in the air when this thing catches fire. So if it's all being cold cut, you had quite heavy wire cutting rigs being moved around. You also had to be able to move the crane rails around on pallet trucks and rollers and the like. So it had to be, again, a very, very stiff structure, but very lightweight and easy to put together. So we came with this modular system where you bolted down this piece here to the node, this piece clipped into it, and then had an adjustable foot, and the rest of it went together like a big Meccano set, and away they go. And it lasted quite well as a structure, and it was really quite stiff. There it is in place. It also had him, if you look on here, you had pockets there for the combi-safe edge protection to be put in place. When it was initially built, there is edge protection, but as you take down as it's dropped down inside the holder and you cut away the tank panels, you've lost your edge protection. So that was all designed in from the very beginning. You can see there the wire cutting systems that I talked about that were quite big and bulky and had to be moved around on there. So we've got all of this ready, sitting in place, and now comes probably the most nerve-wracking part of the whole procedure, which is cutting the roof free. So we blow the piston up to the roof level. So this is the roof, this is the piston, and that's literally been blown up with 2 massive blowers at ground level, a maximum pressure of around 3 kilonewtons per square metre, or 3 kPa air pressure, which raises the piston to the roof. This kind of shows the arrangement. So there's the working platform and the crane rail. So that node point there supports the crane rail and gives the anchoring point for the working platform. And then at the end of the truss, the way this one was detailed, we had to put a steel stiffener into the end of the trusses, and then we had timber blocks between the roof and the piston, and then blow it up and you cut it free, and then you can raise and lower it as required. but it's still a strange feeling to be standing up there when you have nothing but air pressure holding you there. There you go. There you can see one of the stiffeners in place, and then there's the piston just below it, and that's where the stack of timber would be built to then pick that up. I mentioned earlier that the truss, that this holder was struck by a bomb during the war. It actually damaged one of these, the top chord of this truss, and luckily the survey that we had undertaken, or Coleman and Company had undertaken, identified this damage, and it could be assessed to demonstrate that that it wasn't detrimental to the capacity of the trusses, so we could proceed with the methodology that was envisaged. So that touches on a few of the key points. And then we continue working our way down the structure, cutting the panels free, the columns, etc. Get it down to a reasonable height. Everything just landed on the ground. Then remove the root, the cranes, and all the other bits you want to save for future projects, and then you just rip it apart with a machine, as we saw in the video. And this is just a little Google snapshot of how the site looks now. And that is pretty much the end of, well, that is the end of my presentation. So thank you all for listening. If you want any more guidance on temporary works, Josh has listed it already. There's also our website where you can find the recordings of these webinars, and Coleman Group's website, which includes quite a lot of information about their case studies and their capabilities, and is well worth a look.